Ballistics is an increasingly important and complex science that deals with the technical problems involved in hitting a given target in the field and getting the desired tactical results. Sometimes the ammunition we need to do a particular job can be carried to the target or placed in the target's path. Sometimes it can be dropped on the target. But in most cases, it has to be fired or propelled. This involves the solution of three different kinds of problems which are covered by three closely related divisions of ballistics. Interior ballistics is concerned with the launching of the ammunition. Exterior ballistics is concerned with its behavior in flight. And terminal ballistics deals with the action of the ammunition at the target. Let's look first at the problems involved in launching our ammunition with launching devices that are complex, precision-made instruments, but which operate on a principle as simple as that employed in a pea shooter. When the pressure behind the projectile becomes strong enough, the projectile will move. In any gun, howitzer, mortar, or small arms weapon, the pressure behind the projectile is caused by the burning of the propelling charge or propellant, which forms a tremendous amount of gas in the chamber. This pressure is measured in thousands of pounds per square inch and is exerted equally on all surrounding surfaces, but with different results. The forces represented by the vertical arrows have no effect on the projectile. The pressure or force to the right is against the projectile, the most readily movable of the surrounding surfaces, and sends it out of the bore. At the same time, the force to the left is against the gun, which moves in recoil. By making a few changes in our simplified gun, we can see what happens when we launch a rocket. In effect, the lightweight rocket replaces the gun, and the lightweight gas replaces the projectile. The pressure inside, being equal in all directions, forces the gas out of the chamber at an extremely high velocity. At the same time, the pressure exerts an equal force to the left to propel the rocket. Military rockets operate on exactly the same principle as the 4th of July variety. The bazooka also uses the rocket principle, while the recoilless rifle is a combination gun and rocket. The propellant used in guns and most rockets is some form of nitrocellulose, commonly called powder. Modern powder is made in grains, the grains taking many different forms to get the various pressures needed in the many different modern weapons. Apart from chemical composition, grain size is the most important single factor in determining how rapidly a powder charge will burn. Just as wood shavings will burn more rapidly than the same weight of logs because there's more burning surface exposed, so will small grains burn more rapidly than a large grain of the same weight. When small, rapidly burning grains are used, the propelling effect is that of a sharp, sudden thrust. The effect we get from large grains is that of a sustained push. But grain design also affects the rate of burning. In general, there are three types of grain: a large grain with 7 holes, a medium-sized grain with 1 hole, and a small solid grain called a degressive grain. When ignited inside a gun, it burns fast and the pressure rises rapidly. As the burning surface decreases, pressure is generated at a slower rate. Here's a graph to show pressure action during burning. The degressive grain produces a very high pressure quickly, but the movement of the projectile tends to let the pressure drop off rapidly. The medium-sized grain with a single hole is called a neutral grain. In this form of grain, the burning is slower at first, but the burning surface remains constant during the burning period. Thus, the maximum pressure is not as high as with the digressive type, nor does the pressure drop off as sharply when the projectile moves. The large grain with the 7 lengthwise holes is called a progressive grain. Here, the burning surface increases due to the number of holes. The pressure produced is not as high as with the others, but it falls off even less rapidly as the projectile moves. This grain is preferred in modern high-velocity weapons because it gives the projectile a steady push, produces higher muzzle velocities, and has a lower maximum pressure than is possible with other types of grains. There are many other grain designs, the fast-burning powder sheets for mortars, for example. Neutral tube-shaped grains for certain types of rockets, as well as a variety of other kinds, each designed to provide the particular burning characteristics best suited to the weapon concerned. Now let's see what kind of pressure action we need for different guns. When we burn a suitable charge of progressive grains, the pressure is moderate and sustained, sending the projectile out of the bore with a continuous push. This kind of pressure action is just what we need to get high velocity in long-barreled artillery. But now we'll see what happens when we use the same charge in a short-barreled weapon. There's considerable muzzle flash, and the powder continues burning even after the projectile has left the bore, indicating that energy is being wasted. For a short-barreled weapon, a small digressive grain should be used. This builds up maximum pressure quickly to accelerate the projectile in a short space without undue burning afterward. This kind of pressure action is just what we want for low-velocity weapons, such as mortars or pistols. But if we use digressive grains in a long-barreled gun, there's a chance that the higher maximum pressure produced will blow it up. For a rocket, we need a low, steady pressure, so we use a special neutral grain. The low pressure will not burst the lightweight rocket, yet give smooth acceleration. For the V2 and other large rockets, it's better to use certain liquid propellants, mixing them at a constant rate to assure constant burning. In all cases, the propellant must suit a particular tactical purpose. That means providing the desired velocity with a minimum of smoke, flash, and wear on the weapon. Interior ballistics is a highly complicated science, and what you've seen isn't the whole story by any means. But you do know what an important part pressure plays in launching the projectiles. You know something of the effects of grain size and design on gas pressure. And you know the relative burning action of the digressive and other types of grain. In other words, you've got a good idea of why and how a projectile leaves home. Now you're ready to consider exterior ballistics. Exterior ballistics is concerned with the behavior of projectiles in flight. If we could fire a cannonball influenced by no outside forces, it would continue forever in its original direction at its original velocity. If we add the force of gravity, the cannonball follows this sort of path or trajectory. By adding air resistance, we get this result, and the range is shortened still more. To overcome air resistance and get greater range, we might streamline our cannonball, stretching it into a projectile. But look what happens. Our projectile tumbles, and the range is shorter than ever. We need something to stabilize our projectile in flight. One solution is to equip the projectile with fins. The use of fins solves the problem very effectively for mortars and some types of rockets, and the result is much greater range. Having the projectile spin is another solution to the tumbling problem. This, however, causes the projectile to swerve from a straight course, drifting to one side according to the direction of the spin. That isn't as bad as it might seem because we know it's going to happen and we allow for the drift in aiming. To get the required spin, spiral grooves are cut in the bore of the gun and a soft rotating band put around the projectile. The band engages the grooves and the projectile rotates or spins. Although there are many forces affecting the projectile, the most important to remember are gravity, which pulls the projectile down, and drag due to air resistance, which slows the projectile. There's nothing we can do about gravity, but we can overcome the effects of drag to some extent in the design of our projectiles. For instance, by the streamlined windshield on this one. Boat tailing, another method of streamlining, also helps to reduce drag. For long-range fire, we must consider, in addition to gravity and drag, the effects of varying density of the air, the temperature of the air, winds over the trajectory, and the rotation of the Earth. The basic problem of the exterior ballistician is always the same: to study, improve, and predict the behavior of projectiles or missiles in flight. Solution of the problem involves the knowledge of many complex forces, the application of many scientific principles, the use of many ingenious lightning-fast computing machines. The ultimate purpose of all this is to design projectiles and compute firing tables, both of such accuracy that our combat units get the maximum number of direct hits. And that is where terminal ballistics comes in. In terminal ballistics, we are concerned with what happens at the target, with the problem of getting the type of action we want for each different kind of target by the most economical, practicable means. Our projectiles, bombs, warheads, mines, grenades, and so forth are designed to provide different basic effects. By using a large amount of high explosive, we get an effect called blast, making use of violently expanding gases under tremendous pressure. Blast shatters brittle masonry or concrete. It will also twist and tear the metal construction of buildings and vehicles. If penetration is the important thing, we can use a high-velocity projectile with a tough nose and little or no explosive. This sort of projectile will penetrate wood, stone, and up to several inches of steel. By using certain proportions between the weight of the explosive and the thickness of the projectile, we can get fragmentation. Our projectile or bomb breaks up into hundreds of flying fragments. They penetrate like bullets, but leave more jagged, irregular holes. Fragments from bursting shells can do severe damage to personnel and to light structures, such as this plane. Finally, by using incendiary projectiles or bomb clusters, we can start fires to cause great damage in a city, or in a structure or area where large quantities of supplies are stored. Generally speaking, each type of action will be effective against one particular type of target, but a combination will be even more effective. So our projectiles and bombs are usually designed with such a combination in mind. Now, to time or control the action of the projectile at the target, we use different types of fuses. Some of our fuses act on impact, either instantly or after a short delay. Time fuses act a set time after launching. Proximity fuses when they get near the target. Fuse location is also important. In certain cases, we'll get the best results by placing the fuse at the front end of the projectile. In other cases, it works better in the base. Bomb fuses are sometimes placed on the side, and in the larger bombs, more than one fuse is necessary. The fuse type and fuse location determine to a large extent the type of action we get at the target. Now let's consider a typical application of these fundamentals of terminal ballistics in dealing with an enemy plane. Fragmentation is the effect we want. Besides endangering personnel in the plane, flying fragments can wreck the engines, weaken structural members, and may penetrate the fuel tanks, generating enough heat to start a fire. The shell to do this particular job must carry enough high explosive to shatter the shell case and produce high-velocity fragments of the most effective size. Now, what about the fuse for this job? We might use a time fuse, but our best bet will be a fuse of the proximity type, one that will go off automatically when it's near the target. If we're dealing with an armored target or one of reinforced concrete, the first problem is to penetrate. So we need a tough-nosed, armor-piercing projectile that will be strong enough to withstand impact, one that will penetrate without breaking up. Fragmentation is effective after penetration, so a small explosive charge is added. In this case, the fuse must be placed in the base of the projectile and should have a short delay action after impact. The combined effect of penetration and fragmentation gets both the pillbox and its occupant. If we don't have high velocity, we can get penetration by sharply focusing the force of the explosion. This is done by the proper shaping of the high explosive charge. It's up to the terminal ballistician to determine from his experience and his experiments which combination of effects will be the most destructive for each kind of target. And there are other elements to be considered by the terminal ballistician. In all cases, the ammunition he prescribes must be suitable for mass production. It must also be safe to handle, transport, and store. Technically, it must present no impossible problems in any phase of ballistics. The first concern of the interior ballistician is the safe and successful launching of the ammunition. The important point to the exterior ballistician is predicting its behavior in flight. By means of firing tables, this information is passed on to the appropriate using units. They, in turn, must launch the ammunition with full confidence that the terminal ballistician has provided it with the proper destructive potentialities at the target.